Hi guys, my name's Jamin, and this is going to be a quick video on Maxima and Minima problems in mathematics exams. These are also called optimization problems. They're the ones where we're given some sort of physical quantity, and we need to either maximize it or minimize it, or relate it to a real-world scenario in some other way that involves differentiation. These are a really common question type. They're a very common thing to appear in the last question of exams. So that was the last question in 2014 and 15, and the ideas for this topic featured prominently in the final part of last year's exam as well. So this is guaranteed to be worth quite a few marks, and it's guaranteed to be near the end of your exam, which means it's going to be fairly tricky. It usually combines the ideas of differentiation and optimization with a smaller topic like geometry, or perhaps series or trigonometry. It's almost always worth 5 marks plus. Sometimes it can even be getting up into the 7 or even 8 mark range. So you need to know how to do these questions if you're aiming for a band 6. To approach these problems, it's usually a 4-step scenario. Some of these you can break up into smaller steps too. So the first step is always to prove the result. If you have a formula, usually you're not just given it and asked to run. You have to sort of show where it comes from. So you have to prove the result. Now, keep in mind that if you can't prove the result, you should still complete the rest of the question anyway, because the rest of it is just calculus, even if the first part is some tricky geometry or something like that. Step 2 is always to differentiate and put equal to 0. The idea here is to find critical points or potential maxima/minima. However, you cannot assume that those points are the points you're looking for. You need to check whether you found the right point by using either a point either side check or with a second derivative test. And then the final step is always, if you need to substitute the optimal value that you find in step 2 to find the appropriate result. For example, you might find a minimum radius and use that to find the minimum area or something like that. You need to make sure that you're giving the answer they want, not the answer you necessarily find in step 2. To examine this process, we're going to look at an example problem from 2015. Right, so here's the problem from 2015. So the diagram shows a cylinder of radius x and height y, inscribed or placed inside of, I suppose, a cone of radius r and height h. Now, r and h are constants. They're just set numbers, we just don't happen to know them. And this problem obeys a very typical structure for this style of question. We're first asked to show that the volume of the cylinder can be written using this formula. Now, if we can't do that, and I'm going to show you guys how to do it in a second, we could move on to step 2 and just use that formula as gospel without proving it. And the next step is to show that the volume of any inscribed cylinder does not exceed 4/9 of the volume of the cone. So this is an example of a question where you have to actually use the result you're given to do something fairly interesting, and we'll look at that when we get to it. Notice that this is worth 7 marks. This is a lot of marks to be getting into a 1 question in a HSC exam. 3 and 4. 3 marks essentially on geometry and 4 marks on applications of calculus. This is a lot. If you don't get this question, it's a really high chance you're not going to get a band 6. So really important. Let's look at how to approach it. The first step is to prove this result. Now, these sort of questions, it can be really anything, but a lot of the time, it's similar triangles. Similar triangles pop up a lot in this sort of question, and indeed in any sort of geometrical proof. The similar triangles we're going to use to prove this are here. Just drawn it on the diagram there in red, and here's the other one in blue. Now that's a really easy similarity to sort of prove, and we'll get to that when we do it. The first thing to notice, however, is that the volume of a cylinder normally is pi r squared h. The pi r squared gives you the surface area, or the area of the circular base, and then the height gets you the volume. In our case, the radius is x, and the height is y. So, we have pi x squared y. That's always sort of your first port of call. We're wanting a volume, we go to the default formula for volume first. And then we look at our result and we say, okay, what do we have that their result doesn't have? That's always sort of the rationale for what you do next. And what we notice is that we have this y here. That y does not appear in their version of the result. So we need to get rid of it somehow, and that's where similar triangles comes in. Now, to use similar triangles, we're not going to go through a detailed geometric proof. All we're going to write is by considering similar triangles. In a question like this, especially where they haven't given you any sort of labels for your triangles or your points or anything like that, you don't have to go through a rigorous geometric proof. You can just sort of say the sort of result you're going to be using. And we're going to be using similar triangles. And what we're going to say is that the sides of similar triangles are in proportion to each other. So in other words, that the ratio of the short side to the short side is equal to the ratio of the long side to the long side in the two triangles. This is just one way to do it. There is some slightly different ways you can use the same idea. So the ratio we're going to set up is x on r. Notice that that's the small side, which is here, to the smaller side on the bigger triangle, which is here, that's r. And the other side of this equivalency ratio is going to be given by h minus y. Notice that this is the side that you get when you take this big side h and subtract the y. It's given us this little piece in the top of the triangle here, in the red triangle. And then for the blue triangle, it's just h. And the reasoning for that is that the sides of similar triangles are in proportion. So what our job is to do now is that we need to rearrange this expression to get something in terms of y. So to say y equals something, something, something. And that's going to let us substitute into our volume formula. To do this, I'm going to readjust the right-hand side of this fraction, of this equation, ever so slightly. We have h on h, which is just 1, minus y on h. I've just separated it into two different numbers. Once we're there, I can add y on h to both sides. So I get x on r plus y on h is equal to 1. I can then subtract x on r, and what that gives me is y on h is equal to 1 minus x on r. And then to get the result I want, I just multiply by h, and that gives me y equals h bracket 1 minus x on r. That is the result that we're going to use and substitute into our expression. So we'll set up a little box. And so what we're doing is, in our original volume formula, instead of writing pi x squared y, we're going to write pi x squared with what we've just found. So volume is pi x squared times h 1 minus x on r. Now, of course, you don't really need those two sets of brackets. That h can just come out and join the terms out the front. Now we look at the expression that we're given, and we try and tick things off. So we look at what we're given. We have the pi, we have the x squared. We also have the h out the front as well. All we need out the front now is an r. So what we're essentially going to do is divide the front of our bracket by r, or pull a 1 on r out the front of the bracket, whichever way you want to consider it. And when we do that, the first term just becomes, well, I've pulled out 1 on r, so that means that I have to sort of compensate for that by making this term into an r. This was what happens when you divide by a fraction, or pull out a fraction that isn't actually there. You have to compensate by adding something to your numerator. The second term, pulling out the 1 on r, just turns that into an x. And we have the result. That's exactly what we were asked to prove. That is 3 marks. Now we head into the next question to try and get another 4 marks. Right, so we've done step 1. We've proved the result. Now we need to actually use it. So the result we've just proved is that h on r, pi x squared, r minus x, is how we find the volume. Now we've done this because there's now only one variable. Remember that h, r, and of course pi are just constant numbers. The only variable here is x. So we're going to be differentiating with respect to x. To VDX, the best way to approach this, in my opinion, you could also use the product rule, is to just expand this out. And if we do that, we get h pi x squared minus h pi x cubed on r. That's the expanded version of our volume formula. Now differentiating that is quite nice. The first term, the 2 comes out the front, and subtract 1 from the power. Remember, h and pi are just constants, they just sit there. From there, the next one, in a similar way, is 3 on r, h pi x squared. So that is the differentiated version of our volume formula. That's step 2. The next part of step 2 is to put this equal to 0. So to dx is equal to 0. And what that implies is that 2h pi x minus 3 on r h pi x squared is equal to 0. Now we can make a really easy simplification straight away. We can cancel out the h and the pi. They're in every term, just divide by that and they're gone. So what that leaves us with is the slightly simpler 2x minus 3x squared on r is equal to 0. Now we'll rearrange ever so slightly and get 3x squared on r equals 2x. Now I'm going to do something now that you should almost always never do, and that's divide by x. The reason I'm allowed to divide by x in this instance is that this concerns a physical distance. X is a value, it's a value of a radius. It can't be 0. So dividing by x is never going to result in dividing by 0 and getting rid of a solution. I'm allowed to do it only in these circumstances when I'm sure. And to indicate that I've thought about what I've just done, I should indicate that x has to be bigger than 0. I've thought about what I've done. So rearranging this leads to the result that we want, and that's the end of step 2, the value of our variable that could potentially correspond to our maximum volume, which is what we're going to use for the next bit. What it is it's x equals 2r on 3. So that's step 2. Now let's look at step 3. We need to check if this actually corresponds to a maximum volume of the cylinder. Right, so to prove that this corresponds to, in our case, a maximum, we need to do a test. Now in this case, the second derivative is fairly easy to compute. So let's use the second derivative test. Unless your second derivative is nasty, you should use this test. So for us, I've got the first derivative up there. If squared v dx squared, the second derivative of volume with respect to x, is just 2 minus 6x on r. Now what we do is we take our test point, x equals 2r on 3, and we substitute it into that second derivative. And what we do when we get that is we get 2 minus, now the r on the bottom of the fraction will cancel with the r on the top. So it's just 6 times 2/3. So it's minus 4. And so we get a negative value. And remember, a negative value means that we have a concave down curve. So if we have a stationary point where the gradient is 0, as I've indicated there, and the concavity is down, that means that we must have a maximum. So therefore, x equals 2r on 3 corresponds to a maximum point in volume, or to a maxima. So that is the end of step 3. Now for step 4, we need to prove the result that we're asked to prove. Now in this case, that's a bit interesting. We're asked to show that the volume of any inscribed cylinder does not exceed 4/9 of the volume of the cone. So as a first step, let's substitute that x equals 2r on 3 into our volume formula to get a volume expression. So I've just popped our volume formula in the top right there. Let's substitute x equals 2r on 3. We get, in this spot, 4r squared on 9. That's 2r on 3 squared. Then we have r minus 2r on 3 inside that bracket there. Now let's tidy up a few things. This r cancels with that squared on that r. And on the inside of the bracket, that's just going to be r on 3. So we can simplify this expression slightly to 4 on 9. That's from these numbers here. That's promising because that's sort of what we need to prove, right? Then we have h pi r from the start terms here. So that's h pi and the leftover r. And from the inside of the bracket, we have another r on 3. So it gives us r squared on 3. Now, what do we notice about this term? This corresponds to the volume of a cone with a radius of r and a height of h. That's exactly what we had in the question. So that's actually the end of the proof. And all you would do at the end is insert some sort of statement that corresponds to the question. So in this case, I'll just quickly jot one down. Therefore, volume of cylinder is always less than or equal to 4/9 of the volume of the cone. And we can say this because we found the maximum volume, or the x value corresponding to the maximum volume. It gives this value. And since that's the maximum, it's never going to get any bigger than 4/9 of the volume of the cone. So that's how we use it to apply and find our result in step 4. Pretty much any max-min problem can be broken down into something that looked a lot like that question. Prove a result, differentiate, put equal to 0, test your point, and then get a result from that. And that third step of checking the point, that's one that a lot of people forget to do. So make sure that you're checking for the nature of your critical point. You can't assume that it's a max, you can't assume that it's a minimum. Even if you don't really need to in your head, you're like, I know what this is going to be, you need to do it, it's part of the proof. And the other really important thing, guys, is that if you can't do that result at the first step, you can't prove the geometry bit, you can't get what they want you to get, do the rest of the question anyway. Differentiation is something that anyone, or pretty much anyone, will be able to do under exam conditions. The expressions are not usually very difficult. They used to be back in the early 2000s, they're not anymore. So it's something that's very accessible. You can always squeeze a few marks out of that question just by doing a bit of differentiation and putting it equal to 0, even if you can't quite finish it off either. It's all about mark maximization, and what this means is you're not after getting correct answers, you're after marks. So if you can do some working and get a few marks out of that, make sure you do it. And make sure at the end that you're tying it to the correct result. Notice in the question we just did that the answer that they wanted had nothing to do really with the x value. We had to go a fair bit further. So make sure you're doing that where you need to. That's all for this video, guys. If you're after any extra help for 2-unit math, be it with these sorts of problems or any other question you've got, be sure to check out the 2-unit ATAR Notes math forums. You can ask any question you like and I'll be there to answer it. There should be a link to those right after this video is finished. And I'd love to answer any other questions you guys have. Best of luck for the HSC, and I'll talk to you soon.